He's the business development manager at G&D Chillers, an Ingersoll Rand business. He brings a wealth of experience across brewing, biogas, and industrial cooling. A chemical engineering graduate from the University of Texas at Austin, Scott began his career in oil and gas before transitioning to the brewing industry, where he rose to production manager at Falling Sky Brewing and earned his brewing technology certificate from the Siebel Institute. So, Scott, welcome to the program, and thank you so much for talking on chillers with us.
Yeah, great, great. Thanks for having me. So yeah, I mean, if we can, so today we're going to mainly talk about G&D Chiller's R290 product that we put together for um, New Belgium Brewing. So it's kind of a case study. I think that if there's any questions, feel free to drop them in the chat on the side. I'll be paying attention over there, and if anything pertinent comes up, I'll definitely try to answer it as we go. And then at the end, I'll kind of open it up to some further Q&A that's maybe not as specific about this product line, but if you have any other questions about glycol chillers or glycol lines, installation questions, things like that, I'll do my best to answer them as well as I can. So we'll start with a quick background on G&D. We were founded in 1993 here in the Willamette Valley in Oregon. The person who started it had been building refrigeration racks in grocery stores up and down the West Coast for his entire career. He retired and decided he was going to start a vineyard. A lot of Pinot Noir is grown here in the Willamette Valley. So he opened a vineyard growing some Pinot Noir. His neighbor, their chiller, which at the time there was really no packaged chiller manufacturers. They were all kind of just pieced together with refrigeration equipment, separate refrigeration equipment. His neighbor's chiller went out and they asked him if he could build one. And here we are 33 years later. So we've always had a forward-looking focus. So this propane situation, we're definitely way ahead of the curve from the rest of the industry. So we're trying to be leaders. We're trying to drive the industry forward a little bit. So we can move to the next slide, please. Yeah, so New Belgium essentially reached out to us. As some of you may know, New Belgium is a certified B Corp, so they have kind of an environmental bottom line that they're trying to meet, as well as a financial bottom line. So they have a lot of policy that drives them to try to be more sustainable. So they reached out to us asking for they were installing a CO2 recovery system, and they needed a medium temp chiller as well as some low temp chillers. We were able to provide the low temp ones as well, but I'm not talking on those today. But they needed a medium temp chiller to go with that CO2 recovery, and they wanted it to be as efficient and as environmentally focused as possible. So we had been playing with this propane idea, and so we thought that this would be a great place to do it. A little bit of background on why we're even thinking propane. So essentially, in the last 20 years, the main refrigerant that's been used has changed 3 or 4 times. You might remember, if anybody here is old enough, back in the day, they talked about refrigerants putting a hole in the ozone. So there was a lot of changes to move away from ozone depletion potential, so ODP. So we moved to refrigerants that essentially had zero ODP. But now the issue with refrigerants is global warming potential. So the way that global warming potential is defined is 1 pound of CO2 in the atmosphere has a global warming potential of 1. And then these other chemicals are compared to that. So a couple refrigerants ago was R404. I want to say that the global warming potential of that is around 4,500. So it's 4,500 times worse from a global warming side as a pound of CO2. So then we were pushed to have a lower global warming potential within the industry. So we moved to R448A. And then we've been pushed again. So now after R448A, essentially all of the main refrigerants, especially in the industries that people here would be interested in, are called A2L refrigerants, which just means that they're very lightly flammable. But they're not very efficient and they're not great refrigerants, to be frank. I mean, they work fine and there are good solutions with them, but we just see them. Europe has been using those A2L refrigerants for about a decade, and or even a little less, honestly, and they're already moving away from them. So we don't really see the A2Ls as kind of a quote unquote forever solution. So we were trying to be forward thinking and look past that. So that's why we've been looking at the propane thing. We can move to the next slide just to kind of see on this one. It's just Andy Collins, the engineer at New Belgium, just kind of him speaking to how the unit's working for them. It's been working good. They lowered their scope one emissions because of it due to their CO2 recovery system, and then the system itself is quite efficient. The next slide has some pictures of the unit, um, and then moving on to why R290 is the future. So yeah, as I said, the ultra low GWP, so of 3.3. And the other upside to propane is that once it's in the environment, it breaks down. So the GWP 20, which means like its global warming potential after 20 years, is less than 0.1. And then, after 100 years, it's 0.02. So, it breaks down over time. CO2 doesn't break down over time. So CO2 is going to remain at 1. The real issue with those A2Ls I was speaking with earlier is that they have PFAS chemicals, or what you might know of as forever chemicals. Europe has found that there's an increased concentration of those PFAS chemicals in a lot of their waterways, and a big thought there is that it's driven by these A2L refrigerants. I don't know that there's a ton of science proving that at this point, but that's where their head is pointed. So then the other side of it is energy efficiency. As we all know, energy costs continue to go up and up. So people continue to look for more and more efficient solutions. So comparing R290 to a couple previous refrigerants, it's 12% more efficient than 404A, 6% more than 448A, and then 9% more than 454C. So there's other potentials for efficiency gains as well, with heat pumps and different things like that for heat reclaim. So the other reality here is, as I said earlier, we've had to change the refrigerant over and over and over again. If you have an R404A system at your facility right now, if you have a leak, you can buy R404A, but it costs probably 10 times what it did a decade ago, because it's just not being produced in mass volumes anymore, since it's not being installed in new systems. And so that's going to be true for these other products as well. As they move forward, it's just going to be more and more expensive to fix things. So whereas R290, future proof, it's always going to be available. It's a commodity product. It's not a specialty chemical. So it's already quite a bit cheaper than the A2L refrigerants to begin with. So yeah, and we can move to the next slide. So essentially, when it comes to these low GWP solutions, what people start looking at for the future are natural refrigerants. So there's 3 separate natural refrigerants that we can speak to: R290, which is propane, CO2, and then a third one, which is ammonia. Ammonia also has a very, very low GWP. The refrigeration cycle that it uses is different, and then it's also very, very toxic. So in general, in ammonia installations, you have to have really, really heavy SOPs and safety protocols in place. So for the sake of, relatively small scale breweries and things like that, it doesn't make sense at all. It's more so huge industrial facilities that would have ammonia. So that kind of leaves us with R290 and CO2. So comparing those two, you can kind of see on the right, I have some bar graphs comparing propane 454B, which is the current, one of the current standard A2L refrigerants, and then CO2, transcritical CO2, comparing installed cost, energy consumed, cost per year. So propane is cheaper than CO2 by quite a bit. I have a slide later that speaks to the actual values. And then the other upside to it is CO2. What happens with CO2 is whenever it gets above 82 degrees outside, it goes from being, I'll try not to be too nerdy here, but it goes from being subcritical to being transcritical, at which point you lose about 50% of the capacity, and it requires a lot more operational complexity for it to work. So for that reason, the actual CO2 refrigeration cycle looks quite a bit different than what the standard refrigeration cycle looks like. Whereas propane uses the exact same refrigeration cycle. So for that reason, repair is cheaper, and then also the repair parts are quite a bit cheaper as well because they are just readily available in the market since there's really nothing different there. And like I said, whenever CO2 moves to transcritical, you lose about 50% of the capacity. So in Tennessee, obviously it gets pretty warm in the summer. You're above 82 degrees outside a fair amount of the year. So you're gonna be running into those issues a fair amount of the year. On to the next slide. So this is kind of just giving some numbers on the efficiency. So you can see on the right here, we have some sizing software output. That COP over EER, that's essentially the efficiency. I could BTU per hour, so the cooling capacity per watt of power that you have to put into the compressor. So you want that number to be high. So with propane, we're at 8.4, whereas with CO2, we're at 4.2. So it takes twice as much power to get the same amount of cooling with a CO2 system as it does with a propane system, is essentially what that's saying. So the other side of that is that, like I said earlier, the long-term GWP is essentially zero, so that helps. Yeah, all right, I've kind of touched on all those, so we can move to the next one. So essentially, yeah, the main issue with propane is that it can light on fire, right? So CO2 requires really, really high pressure, so there are some safety things around that. And then obviously on the propane side, there's flammability issues. So we had to come up with some solutions to make these systems safe, right? So prime directive there is to make sure everything is safe. So the first thing that we did was reduce the refrigerant charge. So if there's less propane in the system, then there's less flammable potential, right? So the standard 70 horsepower unit that we would have provided for New Belgium in this situation would have 96 pounds per circuit, so 192 pounds total of 448A. Our initial design, we removed some equipment, we moved some things around, took us down to 15 pounds per circuit or 30 pounds total. And then the final design had us at 6 pounds per circuit or 12 pounds total. So 94% total reduction. So essentially in one circuit, you have less propane than you do in like a propane tank that you would hook your grill up to. So really, really, really minimize the potential for danger there. So the other thing that we did there is we separated. So in your chillers that you folks have at your facilities now, you probably have a refrigeration and glycol system that's kind of intermingled with each other. And this one, we separated the propane system or the refrigeration system from the water system or the glycol system. And then we put in a C1D1, so it's explosion proof fan in the refrigeration side that keeps the refrigeration cabinet at negative pressure. So essentially, if there is a leak, the only place for the propane to go is through that fan and out through some ducting to a safe space, right? And then we have a leak detector there so that if it ever gets even close to the flammability limit, it's going to pull power from the entire unit. So, and the other reality is we're pulling 3 or 4, actually maybe more than that, it's probably closer to 10 air turnovers per minute in that space. So the possibility of it actually ever getting to a flammable level is near zero, just because you're pulling out any small leak right away. So once again, pretty safe. And then serviceability. So as I said earlier, the CO2 side of things, still on that. Yep, there we go. Sorry. So with the CO2 side of things, it is difficult. You have a lot of technicians look at it. It's kind of a spaghetti factory of pipes in the CO2 system. Whereas with these propane systems, they're actually very, very simplified and straightforward. And the real issue that we're running into now is there's lack of regulation or certification nationally. So we've sold quite a few of these propane systems, but essentially we have to talk to the local jurisdiction, like the fire marshal, on every single one of them. to ensure that everybody there is happy and feels confident in the safety um, factors that have been installed. On the next slide there. So yeah, installation efficiency analysis. So essentially, whenever we did this slide the first time, it was back in May of last year. So we have a full another year of running, and this has just remained true the entire time. Um, so we've had zero downtime in that time, knocking on wood over here. And then still have had zero downtime in the full year that we've had it running as well. And we were able to see that at these brewery conditions, we did get this 8.4 EER. We actually even got a little bit better than that in our real world efficiencies. You can see here that we were able to get 8.85 as compared to the 8.4 that was expected in the sizing software. So we were able to actually see what was expected, which is always nice to see. Moving on. So future plans for G&D, we have already started installing these in other industries. We have quite a few in some food processing facilities. We have a handful in some chemical plants. We've got some that are being built right now that are going in wineries, and we have some being built that are going in dairies. So there's quite a few folks that are adopting these. Yeah, and then we really need the real push right now is we need to be involved in policy making so that we can make things easier and really get these installed in a wider base. And then on to the cost analysis for this specific project. So R290 is a little bit more expensive to install than your standard A2L, essentially because of the safety features that we have to put into place. So leak detectors, that fan that pulls air through. And then at the installation site itself, you need to run a little bit of piping and ducting away from the unit to a safe space. So there is a little bit of increased cost compared to the A2L options. That being said, it's considerably less compared to CO2. You can see in the bottom right, we kept 454C as the one-to-one basis, so that's got 100%. The R290 is 135%. This was a year ago. We've gotten that number down closer to 115% now. And then transcritical CO2 is about 3x. And that number is not going down essentially because of the operational complexity required. And you can also see here that the estimated energy cost is several percent lower for R290 as opposed to R454, and then once again about half of what it was expected for CO2. So on to the next one. It's just kind of a quick summary. Tomorrow proof, extremely low GWP, no PFAS, no ozone depletion. So very, very efficient. So we definitely feel like this is kind of the future for process chilling in North America, especially considering that CO2 has such issues at high ambient temperatures, and in much of America, obviously, it runs at higher than 82 outside quite a bit of the year. So, but yeah, if there's any specific questions, now would be a good time.
Yeah, I've got a couple questions that came in.
Yep.
Let's see. It says, so this is sort of more broad, like what are the biggest sustainability opportunities when improving glycol chilling systems in breweries and distilleries?
Yeah, I mean, I think that things have gotten a lot better in the brewery and distillery space as far as installation goes, but let's say even 5 years ago, the level of education within these spaces, especially the craft spaces, was a lot lower. So the biggest thing that you can do is insulate your glycol piping. So a lot of folk, I've been in a lot of breweries that just have glycol pipes that are sweating because they're not well insulated. And so essentially anytime you see condensation on a pipe, that's heat coming into the system, quite a bit of heat, honestly, coming into the system that the chiller has to keep up with, right? And so that's going to reduce your efficiency by quite a bit. Another thing that you can do is like CLTs or cold liquor tanks, things like that can help quite a bit because you can cool down quite a bit of water overnight as opposed to using the chiller directly to cool your wort or mash. That's definitely can be helpful, just spreading it out over time. Um, and then just staying on top of your preventative maintenance. So really what can happen a lot of the times is if your condenser coil on your chiller gets dirty, then that's going to cause the heat transfer efficiency of that condenser to go down considerably. And so essentially whenever that happens, you have higher condensing temperatures, so you're going to have more operating issues, but also that means that it requires more power for the system to run at the same capacity. So um, so keeping your condenser coil clean is another solid move.
Yeah, this question, honestly, I think you maybe probably answered it right here, but it says, how can smaller craft producers begin making improvements if they don't have a large capital budget?
Yeah, so I would say make sure your pipes are insulated. If they aren't, then just stay on top of cleaning your condenser coil. Installation is important too, right? So like if you install your chiller too close to a wall, or a lot of times folks will actually install them backwards, where the outlet air actually is shooting straight into a wall. If that happens, you're going to get recirculation of that hot air, and that's going to cause issues during the hot months for sure. And also will cause it to be less efficient during the cool months, even. So making sure the install is done correctly, and insulate your pipes, and then, yeah, like I said, stay on top of cleaning the condenser, which is really, really easy. I mean, you can pay a refrigeration technician, let's say couple $100 3 or 4 times a year to come out and do that, and they'll check on other things while they're there. Or you can go and you can buy specific, you know, it's the exact same thing as your air conditioner, right? So it's just air conditioner coil cleaning stuff, so you can go and make sure that the coil is clean, keep any debris out of it, that kind of stuff. Definitely don't use a pressure washer. That's something that people do from time to time, and that folds over the fins. And whenever that happens, your condenser essentially is not usable anymore. So don't do that.
So this question, I think you might have already answered it as well, but it says, what are the most common inefficiencies you see in glycol systems at breweries and distilleries? So I'm assuming like, what you've already mentioned,
Yeah,
not
and then
insulating.
another one is being undersized. Essentially, a lot of times people are, whenever they're buying it on the front end, they don't think through expansion or the ability to expand, things like that. And so a lot of times what will end up happening is the chiller gets overtaxed, especially during the summer, whenever it's less efficient to begin with because it's just hot outside. And then at that point you start having operational issues, which are frustrating, but also cause you to be less efficient too.
Let's see, this one just came in. It says, are there tax credit or other benefits from installing a CO2 capture or propane chiller system?
I mean, that would be Tennessee specific, so I'm not 100%. I know that there definitely in Colorado, where New Belgium is, there was definitely things in place for the CO2 recovery system that helped, that pencil out from a not just their B Corp standpoint, but from the overall money side standpoint. The other reality is, whenever New Belgium was installing that system a handful of years ago, or starting to plan that system, I should say, there was a major CO2 supply chain issue. So I don't know if anybody here really remembers that, but it was really, really hard to get CO2. If you didn't have like a set contract, you were kind of, SOL essentially on being able to get CO2. A lot of small producers struggled during that time. And then the CO2 price went through the roof as well. So with this CO2 recovery system, they're able to take CO2 off of their fermentation and off of, after they push push a product out of a fermenter or out of a bright using CO2 to push, they're able to reclaim that, liquefy it, and then reuse it to carbonate or push product later as well. So there's some operational benefits outside of just the tax benefits. But short answer, yes. I would say on the propane side right now, no, because there isn't this widespread acceptance yet.
Yeah, and we can, for this Tennessee specific, Mark and I can look into some of that and see if there's anything that out there that we're currently unaware of. So we'll do some research and reach back out.
Yeah,
Another.
we can check it
Okay.
in an update. I just wanted to piggyback, Caleb, not to interrupt, but on one of these questions when it comes to chillers specifically, is there any recommendations of combining chillers to do maybe some of the fermentation side of things as well as cooling, maybe like a cold storage unit as well, or do you recommend to separate those out?
Yeah, so in general, I recommend separating those. The reasons are a couple fold. One, um, it doesn't put all your eggs in one basket. Refrigeration systems can be finicky sometimes. So, if you have it all on one system, then everything's out at once. It makes it a lot bigger emergency. But that's not really the main driver. The main driver is cold storage rooms. That type of refrigeration is not a niche product like a glycol chiller. That's a widely available commodity product. So you can buy direct refrigerant cold room equipment for very, very cheap. And since it is direct refrigerant, it's going to be more efficient, right? So the glycol is kind of a middleman that we need in this situation since we're pumping it through a bunch of different tanks and things like that. You can't just send refrigerant directly to those efficiently or really in a way that promotes the equipment lasting very long. So you end up having to use glycol instead. Whereas in the cold room you can just use direct refrigerant. It's very very efficient. So in general, I would say don't. But sometimes since there are distinct sizes of chillers, so like maybe you need 15 horsepower of chiller, right? And we offer a 14 horsepower unit and then a 20 horsepower unit, right? So the 14 horsepower unit's not going to do it because you need that one extra horsepower. So we got to put you in the 20. So at that point, you have some extra capacity already, so you might as well use it. So in that situation, it makes a lot of sense to go ahead and use a chiller. The other situation where it makes a lot of sense is in a lot of wineries, where essentially you're fermenting for very short periods of time over the year. You're not fermenting year round for most wineries, and then you have barrel rooms that you need to keep conditioned. So during the summer, so essentially during the summer you're not fermenting, so you can use your chiller to keep your barrel room at the temperature you want it because you're not really using it to ferment. So
Let's see. That's one more that came in. Says, what role do refrigerant choices play in making chiller systems more sustainable?
yeah, so I mean, essentially, it has a lot to do with either the efficiency side. So, like I said, um, you know, whenever you're choosing a refrigerant, that that essentially sets how much power it's going to take to cool. So your brewery, your winery, your distillery, it takes X BTUs. You're kind of set, right? Because you want to operate in a specific way. And so then the only thing that you really can control in that situation is the refrigerant choice. So if you choose a less efficient refrigerant, your power bill is going to be more. And then due to that, you're going to have to use more resources to create that power. So the sustainability goes down. And then the other side of that is leaks happen, right? I mean, it's a situation where you try to prevent as many leaks as possible. The EPA actually assumes that every pound of refrigerant that is installed in a refrigeration system or HVAC system is going to leak. That's their assumption. Um, Not 100% true, but that is the assumption that goes into it. So, whenever if you were to release a higher GWP refrigerant, then obviously the global warming potential situation is higher in that. So, choosing a lower GWP refrigerant helps us on the global warming side.
All right. If anybody has any more questions for Scott, send those in. And then also, you know, um, if you're eating dinner later tonight, you're like, man, I wish I would have asked Scott this. Feel free. You've got my email and Mark's email, and then you will be receiving the follow-up email that has the link and the slides and everything. So um, if at any point you think of something that you want to ask Scott or Mark, uh, make sure to email that to us, and we can work on getting that that answered for you. So I think that does it. I know we're a little early, but nobody's ever sad about getting a little bit of time back. And so, Mark, I was going to pass it on to you to sign us off, and then we'll be good to go.
Great, thank you. Once again, thank you so much, Scott, for joining in on this conversation with chilling systems and glycols. I think this is a very important topic to discuss, especially in the spirits industry when we're trying to save as much money as we possibly can. And so I think some of the practical tips you provide are super helpful. This is something that we're trying to incorporate more in depth with our sustainable spirits program as well. So if anyone has any questions or technical assistance questions relating to this, we can get you into contact with the right experts, or we can provide some high level resources as well. But again, thanks you everyone for joining. And if you want to reference this, look out for an email next week. We will post this for everyone to view, and they will also be available on our webpage in the near future. But before we take off, we got 3 follow-up questions just to see if anyone's improved their knowledge relating to glycol and chiller systems.
Yeah, and so just like before, on your right hand side, the first question should be up. So feel free to click on over. It's basically asking similar questions that we did at the beginning. This first one is, after this webinar, how would you rate your understanding of the benefits and challenges of using R290 in chiller and glycol systems? 1 star meaning not familiar at all. 5 stars meaning pretty confident or very familiar. Good deal. Go to the next one. Oops. Wrong one. So which benefits of our 290 systems stand out most to you after today's webinar? We got lower global warming potential, and you can click as many of these as you as they stand out to you. So lower global warming potential, improved energy efficiency, lower installed cost in CO2 systems, familiar components for service technicians, or future regulatory compliance / tomorrow proofing. And I like that, Scott. I think I'm going to use tomorrow proofing in the future for some of my presentations.
Yeah.
All right. Appreciate that. And we will go now to final one. As a result of this webinar, which actions are you most likely to take in the next 6 to 12 months? Once again, you can choose as many of these as you feel like that you might take into action at your facility. And I'll read those off. Explore R290 or other natural refrigerant options. Review my current chiller glycol systems efficiency, which I think everyone should do if they haven't. Talk with leadership or vendors about sustainable cooling upgrades. Learn more about safety and regulatory considerations. And then I am unlikely to take action at this time. So once again, we really appreciate you guys doing this. This helps us out a lot. Just having metrics for our educational resources that we put out. We appreciate everybody being here, and see any more questions. But if you've got those, shoot them my way, and be on the lookout for our follow-up. Thanks, Scott. Thanks, Mark. Everybody have a great rest of the week.
Thanks, everyone.